Great.
Right, we've got a worked example here for probability functions, and this is about a discrete random variable that's defined by this set of rules here. Let's have a look. The discrete random variable x takes values 1, 2, 3, and 4, and 5, and its probability distribution is defined as follows. Okay, so the probability that the random variable equals a particular number depends on the number. So it's some unknown value a for x equals 1, and then it's half of the probability that x equals 1 minus x for 2, 3, 4, and 5. So what this is actually doing, it basically is we're starting off with a value, and then every subsequent value is half of that up to 5. Okay. So we've got to show that a equals 16 over 31. So once we've drawn this table out here, so we can fill this in, so the probability is a, and then it's half of that. So I think we can probably see from that, if we were to kind of add all these up, we've got an equation in A, and we can show therefore that A equals 16 over 31. The way I've done it here, basically I've sort of said, well, let's add all these up, and I've just done it as a series here. A into 1 plus a half squared plus half cubed plus a half to the power of 4. That's all going to equal 1. And then I've used this identity that we should be familiar with from algebra. That's the sum of 1 plus x, etc., up to x to the power of the n equals this identity here. Could reverse the signs on the upper and the lower, which we would normally do if we knew that x was bigger than 1. For x less than 1, we tend to write it this way around, but no matter, it comes out the same thing. So that basically is it. So once we've evaluated that, and I say we don't have to do it this way, that's just the way I've chosen to do it, we're going to get an equation in A, and that's just going to give us A equals 16 over 31, 16 31ths. Okay, and then it goes on. Well, it says that the discrete probability distribution for x is given in the table. Right, okay, well, we've now that we know what A is, then we can now calculate what the other ones are anyway. So we could have done that for ourselves. They've given it to us, but so we could have done it ourselves. Find the probability that x is odd. All right, I'm just going to wind down the table here. Okay, so the x is odd. Well, that's the probability of this plus the probability of this plus the probability of this, isn't it? So that's not too difficult. 21 31ths. And then 2 independent values of x are chosen, and their sum s is found. Find the probability that s is odd. Right. So let's have a look. This is an addition table here. So this value here represents the first value is 1 and the second value is 2. Okay, so that's the probability of that. Now, bearing in mind that all these probabilities, because they're independent events, it's going to be something divided by 31 times something divided by 31. So all the probabilities are going to be over 31 squared. So just to make this table a bit simpler, I've just put a little kind of caveat up here, all divided by 31 squared. So the probability of 1 followed by a 2 is 16 times 8 divided by 31 squared. Essentially, it's 16 divided by 31 for a 1 on the first selection, and then 8 divided by 31 for the second selection. All right, so we go through and populate this whole table on that basis then. So so we've done all that. So and we're looking for the probability that S is odd. Well, actually, I've done it for all the odd for all the odd sums. So that's 1 plus 2, that's 1 plus 4, and so on. I'm not bothered with the even ones because at this stage we don't need it. Okay, so if we add all these up, and I've added them up, and again, all these numbers are divided by 31 squared. All these rows come to 428, so it's 428 divided by 31 squared, which equals that. So the probability that S is odd is 0.4454 to 4 decimal places. Right, okay, so that's that one. Find the probability that S is greater than 8, given that S is odd. Right, now this one is basically hinting at some conditional probability here. And so really what we're looking at is what's the probability that S is greater than 8, given that it's one of these, because we've selected out the odd ones, haven't we? So what we've actually done is we've kind of constrained the probability space. So we want to know the probability relative to what's left. Well, what's left is this 4454 here, which is 428 over 31 squared. So so let's have a look. So restating Bayes' rule, this is Bayes' rule, probability of A given B is equal to the probability of A intersection B divided by the probability of B. So now if that's means nothing to you, then I suggest you go back to the probability section and look through the conditional probability videos there. So but essentially these are the things that we're interested in. X is greater than 8 and odd, and this is the space that we're confining ourselves to, so effectively dividing by this. Okay, so the probability that S is greater than 8 and S is odd, essentially these two. Well, 2 31s, 2 31 squared over 31 squared, and 2 over 31 squared here. So that's that. So that's the numerator. This is the denominator, or at least it's the reciprocal of the denominator. The probability that S is odd, we've worked that out. It's 428 divided by 31 squared. And of course, we're dividing by this fraction, so therefore, if we multiply by its reciprocal, that's what we're going to get. And which is okay, because the 31 squares will cancel out, and it will leave us with this fraction 4 over 428, or 1 over 107. So that is how that works. Right, continue. And part 5. Find the probability. Oh, hang on a minute, I missed out a bit of the question. Sheila sometimes needs several attempts to. I had to look back on this question. I thought, oh, it hasn't mentioned Sheila before. I just brought Sheila in at this stage. Sheila sometimes needs several attempts to start her car in the morning. She models the number of attempts she needs by the discrete random variable y, defined as follows. Right, okay, well, we have to kind of get our brains around this a little bit. It's basically saying that the probability of 3 attempts is half of the probability of 2 attempts. So we can see that. So it's basically the same idea, but in this case, it doesn't say it's limited to 5, does it? So, so if we actually kind of work it the same way, I mean, let's call the probability of one attempt A, which is what we've done in the first part of the question. Then what we've effectively got is we've got this infinite series here. Okay, so which actually is one of the reasons why I used the series previously. So this is an infinite series, and it's going to add to 1. Now, when we've got an infinite series, basically our nth term is infinity. All these terms are less than 1. So our numerator basically becomes 1 minus something less than 1 to the power of infinity, if it can put it that way. And that's just going to be equal to 1. So it's 1 over 1 minus a half. Okay. And we know that to be 1. So that implies that A is equal to a half. So it's a similar sort of series, except this is infinite. Of course, it goes half, quarter, eighth, 16th, 32nd. These are all the probabilities going on, stretching on into infinity. So it says find the probability of 1. So we've done that because we found that's what A is. That's the first term in this sequence. So the probability that y equals 1, she starts it on the first attempt, is a half, 50-50. Not very good, really. I think about time she sold that car. Anyway, here we go. So that is that. And then finally says, give a reason why one of the variables, X or Y, might be more appropriate as a model for the number of attempts that Sheila needs to start her car. Yeah, well, Y suggests that you've got an infinite number of tries, doesn't it? There's some probability associated with having, with being able to succeed on the 20th attempt. Yeah, you're going to have a flat battery before then, aren't you? And the truth be known, you'd probably get maybe 5 attempts before you're going to have to give up because the battery's flat. So I think X is probably more appropriate. Okay, so that is it. I mean, it's a kind of a bit of a messy problem, really. But I think a lot of the difficulty actually is in just being able to unpick these statements here. But anyway, hopefully it has been useful, and we'll see you next time.